My name is E. Today, I'm going to talk about improved hardness of BDD and SVP under gap SETH. This is joint work with Huck, Bennett, and Peikert. So the problems BDD and SVP are known as the lattice problems. So I will start with introducing the notion of lattices. Roughly speaking, a lattice is a regular grid of points in space. And more formally, a lattice L of rank n is a set of all integer linear combinations of a basis B1, B2 till Bn. Here in the figure, we could see an example lattice generated by the blue vectors B1 and B2. The lattice consists of all the black dots that are the integer combinations of the bases. And we could also observe that different bases could actually generate the same lattice. Study of lattices is promoted by lattice-based cryptography. Nowadays, we are approaching more and more practical quantum computation, and it turns out that attacker with quantum computation can actually break crypto systems that are based on number theory. One solution to this problem that people find is to use lattice-based cryptography, since people believe that some lattice problems are hard to solve even with quantum computation. Currently, the state-of-the-art attacks to the lattice-based crypto systems are based on solving exact or low approximation factor lattice problems, such as the SVP problem. Based on this fact, we also face another problem that whether the attacker can solve these lattice problems in 2 to the n or 2 to the n over 10 or 2 to the root n time has actually a huge impact on the security. Our work tried to address this problem by showing fine-grained hardness results for these lattice problems. The first lattice problem we consider is the shortest vector problem, SVP. In SVP, an important geometric property of lattice is considered, that is the shortest LP norm of non-zero vector in the lattice L, denoted by lambda1 of L. Taking the previous example lattice, we could see that the red vector B2 minus B1 is the shortest non-zero vector in the example lattice, and its length, or the radius of the red circle, is the quantity lambda1 of this lattice L. The gamma approximate SVP problem in LP norm is the problem where we are given a lattice L, and the goal is to decide whether lambda1 of the lattice L is at most 1 or at least gamma, the approximation vector. Another lattice problem we consider in our work is the bounded distance decoding problem, BDD. The BDD problem in LP norm with relative distance alpha is the problem where we are given a lattice L and a target vector T with the promise that the distance from the target vector T to the lattice L is at most alpha times the lambda1 of L. And the goal in this problem is to find a closest lattice vector to T in lattice L. Note that here, a smaller alpha factor corresponds to a stronger promise that the target is closer to the lattice, and this smaller alpha corresponds to an easier problem. In the figure below, you could see an example of the BDD problem for Euclidean norm p equals to 2 and alpha equals to 0.6. In this example, if the target vector t is within the green circles, for example, if we take the red dots as target vector t, then the goal is to find the closest lattice vector to t. And if the target is outside all the green circles, then the BDD problem does not care about that case. Previously, we've seen that our goal is to show fine-grained hardness of lattice problems, and a standard approach to fine-grained hardness is to assume exponential time hypothesis, ETH. The hypothesis ETH assumes that 3 SET cannot be solved in 2 to the little o of n time. A stronger variant of ETH, known as strong ETH or SETH, assumes that k SET cannot be solved in 2 to the 1 minus epsilon times n time. Besides, we also have the gap variants of ETH and SETH, where we consider the gap 3 SET and gap k SET problems instead of k SET and 3 SET. Moreover, we also have the randomized and non-uniform variants of all the ETH variants above, where randomized or non-uniform time is considered instead of deterministic time for solving these problems. To remark, as the name suggests, the strong ETH is no weaker than ETH, and gap ETH and gap SETH is no weaker than respectively ETH and SETH. Moreover, the randomized variants are no weaker than plain variants, and the non-uniform variants are no weaker than randomized variants. In our work, we exploit the power of these different ETH variants and show stronger hardness results for the BDD or SVP problem under stronger variants of ETH. Even if we do not care about lattice problems, this also shows that we have interesting applications for all these different variants of ETH. More specifically, to show the fine-grained hardness of the lattice problems, we reduce SET on n variables to the lattice problems in rank C times n for some constant C. Our first group of results are ETH-type hardness results for BDD. Our first result is that BDD cannot be solved in 2 to the little o of n time for any norm p and any alpha that is at least some constant alpha kn, which is approximately 0.98 under non-uniform gap ETH. Our second result is similarly that BDD cannot be solved in 2 to the little o of n time for any norm p and any alpha that is at least the quantity alpha double dagger, while this time under randomized gap ETH. Here the figure shows a comparison of our result 1 and result 2 to the previous bound in the work BP20. The blue dashed curve shows the previous bound in BP20, and we could see that our result 2 always improves upon the previous bound. And moreover, our result 1, which is the horizontal line, improves upon the result 2 for small enough p. To remark, in BP20, randomized ETH instead of randomized gap ETH is assumed. So strictly speaking, all the results are not comparable. However, we indeed shows that with stronger assumptions, we could show stronger hardness results for BDD. Our result 3 is an SETH-type hardness of BDD. It says that BDD cannot be solved in 2 to the n over c time for any norm p that is not even integers, any c larger than 1, and any alpha larger than alpha dagger, under non-uniform gap SETH. In the figure below, we could see a comparison of our results to the previous bound in BP20. The blue dashed curve shows the result in BP20 for C in the range 50 to 200. The bound in BP20 for this range looks almost the same at the scale of this plot. We could see that our result 3 improves upon the previous bound for small enough p and large enough c. Also similarly, in BP20, it only assumes randomized SETH instead of gap SETH. Our last result, result 4, is an SETH-type hardness of the problem SVP. It says that SVP cannot be solved in 2 to the n over c time for some constant gamma at least 1 for any norm p that is at least about 2.1 and not even integer, and any c at least the quantity Cp. The result assumes randomized gap SETH. We remark that here the quantity Cp approaches 1 as p goes to infinity, so that we essentially have 2 to the n hardness for SVP as p goes to infinity. Here is a summary about the hardness of the SVP problem. The previous work, AS18, has the similar results of 2 to the n over Cp hardness for SVP problem, but only for the exact version of SVP problem. In another word, for gamma equals 1. We improved this work by showing the same 2 to the n over Cp hardness for gamma equals 1 plus epsilon, some small constant. Similarly, in AS18, it only assumes randomized SETH, while we assume randomized gap SETH. Moreover, we have NP hardness of the SVP problem for any constant. And when gamma is some large constant, we have 2 to the 0.8 n algorithm. For gamma being some large enough polynomial, we have a better exponential time algorithm. And finally, for gamma being some exponential function, the SVP problem is easy to solve by the LLL algorithm. In the proof of our results, a core technique we use is the locally dense gadgets. A locally dense gadget consists of a lattice L dagger in rank n and a target vector T dagger. For the locally dense gadget, we consider 2 point countings in the gadget. We denote by n short the number of lattice vectors of length less than 1, and by n close the number of lattice vectors of distance at most alpha close to the target T dagger. We say that L dagger is locally dense at T dagger if n close is at least nu to the n times n short. That is, if we have exponentially more close than short lattice vectors. Here, the important quality parameters of locally dense gadget is alpha close and nu. In the picture below, we can see an example of locally dense gadget. Here, the rank n is 2, and the lattice is the 2D integer lattice. The target is the all half vector. And we could see that by picking alpha close to be 1 over root 2, we have 4 close vectors to the target T dagger, while we only have 1 short vector, that is the origin, which has length less than 1. So here, we have 4 times more close vectors than short vectors. Our main theorem for the BDD problem tries to transform a locally dense gadget to the hardness result for BDD. In particular, if there exists locally dense gadgets L dagger, T dagger with parameters alpha close and nu, then for the BDD problem, we show that it cannot be solved in time 2 to the little o of n for any alpha that is at least alpha close under gap ETH variance. Here, whether we have randomized or non-uniform gap ETH depends on whether our gadget can be constructed efficiently. Moreover, we show that BDD cannot be solved in 2 to the n over c time for any alpha that is at least alpha close plus some epsilon term of nu to the c minus 1 under gap SETH variance. Here the epsilon term tends to 0 as nu or c tends to infinity. Recall that for smaller parameter alpha, the BDD problem is easier, and thus the hardness for BDD problem is stronger. So here, if we have smaller alpha close parameter or larger nu parameter, we get stronger hardness result for BDD problem. This is intuitive since smaller alpha close parameter and larger nu parameter corresponds to a somehow denser gadget. A result by Vladit shows that there exists lattice L dagger with exponential kissing number. That is, the number of lattice vectors of length lambda 1 is at least 2 to the ckn times n, where ckn is some explicit constant that is about 0.02. Here are pictures showing the kissing number for low dimensions. Based on this result, we construct locally dense gadgets by picking exponential kissing number lattice as the lattice L dagger and set T dagger to be 0. By doing this, it can be verified that we get gadgets with parameter alpha close equals to 1 and nu equals to 2 to the ckn. Moreover, we also use gadgets from the integer lattices by setting L dagger to be d to the n and T dagger to be the all T vector. This is similar to what we've seen on the previous slide. Using these locally dense gadgets, we instantiate our main theorem and get our results. We start with result 3. The result 3 says that BDD cannot be solved in 2 to the n over c time for all alpha larger than alpha dagger. For result 3, we use the kissing number gadget. Recall that it has the parameter alpha close equals to 1 and nu equals 2 to the ckn. By the main theorem, we immediately get alpha dagger to be 1 plus the epsilon term. Our result 1 also used the Kissing number gadgets. The result 1 says that BDD cannot be solved in 2 to the little o of n time for all alpha that is at least alpha kn. In result 1, we try to decrease alpha close for Kissing number gadgets. Previously, we set T dagger in the Kissing number gadget to be exactly the origin 0, while here we try to perturb T dagger away from 0, while keeping the parameter nu to be at least 1. Eventually, we get alpha close approaching the quantity alpha kn, which is defined to be 2 to the minus ckn. Our result 2 used gadgets from integer lattices instead of Kissing number gadgets. Result 2 says that BDD cannot be solved in 2 to the little o n time for alpha that is at least alpha double dagger. In result 2, we try to minimize the alpha close parameter in gadgets from integer lattices, subject to the constraint that nu needs to be at least 1. And we get alpha double dagger as the optimum. Finally, our result 4 is for the SVP problem. It says SVP cannot be solved in 2 to the n over c time. For SVP problem, we have a similar theorem based on locally dense gadgets as we had for BDD. And for result 4, we used the same gadgets from integer lattices as in result 2. That's the end of my talk. Thanks for watching.